Okay, hi everybody. As you can see probably, I'm working for Apostera, but this topic is not completely about my work in Apostera, it's about my master thesis that I finished just a month ago. So now I have a disclaimer for you. Please, if someone here can be offended by proof of evolution theory, go out. Nobody? Okay, then we can start. So in my talk, I will quickly overview existing methods like reinforcement learning, Salimans evolution strategy, and Uber neuroevolution. And then I will tell you about the essence of my master thesis. It was presented at ICDC AI in this year, and the paper and the documents will be published in 2 months by Springer. So before this time, I cannot publish anything by myself, sorry. So first, quickly recap, what does reinforcement learning do? We have some agent that can act in some environment. And this agent can execute actions, and it also receives a state of the environment. For example, it's your robot's vision, and it can execute actions and have a reward. The reward can be either every step, or in the end of the round, it is a sparse and general reward. So, and as agent, we define some policy function that is usually a neural network that takes a state and then it executes an action. And usually in contemporary robotic tasks, it has over 1 million of parameters. So it's pretty hard task. In my talk, I will talk about the reward function and also the fitness function for evolutionary strategies. That is a sparse reward, and it goes at the end of the episode as a sum of all the rewards. You can see it just right here. And first great topic was developed in 2017 by Tim Salimans, and he developed a neuroevolution algorithm that is actually nothing to say about the evolution, but it is just a convenient name. The overall idea was to sample many policies with Gaussian noise applied to the parameters, and then evaluate everything in environment, and then take the weighted average. And why does it work? It works as approximation of stochastic gradient descent, and it only works because you need to sample really many these policies. These policies you need to sample from 100 to 10,000 to stable work. And the main goodness of this paper was it is just embarrassingly parallel. You can run every evaluation on every single core or GPU or even over the network, and you need to share only a single scalar, the reward from every agent. And then you can rinse and repeat, and you can go everything. And it will somehow converge, and here's proof why this works, and here is a demo. So as you can see, you start in some initial condition, and then you sample a Gaussian noise around this point, and then you evaluate every single generated point and weight it with a fitness function. So here's blue is bad and red is good, and then you take a step in the direction of your weighted fitness function. After that, you go after and after and after, and somehow you will converge to this thing. And here you can see the proof. Why does it work? Why is it an approximation of gradient descent? So it works as we expand our function to a Taylor series and use the property of Gaussian noise that every odd moment is equal to 0. So this, after we substitute this to this, we eventually get this, and this is an approximation of stochastic gradient descent, for exception that it can work for non-differentiable policies, it can work highly parallel, and it is really better. But the problem is it is very sample inefficient. For example, if you have 10,000 processing cores, it will be really outperforming everything. They learned an Atari game for only 10 minutes with this algorithm from pixels. And also, it highly depends on policy parameterization. So the policy is our agent. And if we parameterize it too uncertain or something in very blue region, it will take forever to complete the convergence. And that's how it works. And the also recent paper that was released in February of this year is a Uber Neuroevolution. And it is even more great than Salimans. And it resembles genetic algorithm, but only without crossover function. So the overall idea is here also simple. They present two possibilities. The first one is to make safe mutations with rescaling and safe mutations with gradient that you will see later. And the main idea of these safe mutations is that apple never falls far from the tree. So we select the best individuals, so our policies that are parameterized somehow, these are neural networks, and we introduce some Gaussian disturbance to their genomes. For every gene or every weight in neural network, it will be the new delta that is considered as delta direction and delta scale. And then we calculate for everyone their divergence from the parent neural network, so disturbed and undisturbed neural networks. And then with just linear or binary search, we find how to make this divergence small enough that we don't disrupt the behavior of the agent in the environment. It was the first their attempt, and it works great for non-differentiable policies or non-differentiable neural networks, or every controller. If you want, you can make an, for example, in control task a PID controller and evolve it with this algorithm. And the second variation of them was safe mutations with gradients, and they extend the gradients of weights with respect to output, not the error, to define how sensitive is each parameter to disturbance. And then, given this sensitivity, we can evaluate and mutate it more effectively. Also, they provide three methods of evaluating. The first one is a clean way to find sensitivity. It is a way to find a gradient with respect to outputs of neural network over batch. And then we have a sensitivity of each weight. And it is a precise moment, and it is very slow in our contemporary GPU-oriented frameworks. So they also say that we can calculate it approximately, but it will be really faster because we don't need to average over batch and to calculate absolute value, which is slow. And this is really faster and works as well fine. And also they introduce an approximation and a better version for approximation of stochastic gradient descent using the second order derivative. And with this Hessian of divergence multiplied by divergence and directions, they get the new sensitivity with respect to desired divergence. And this converges even more faster, but is not that stable. Можно видео включить? Вот это. And now here's a video from their blog, how does it work, and it's very good. Okay, video is on its way. Okay. So you see the apple never falls far from a tree, and all the agents are quite stable and go to the finish line through this maze. Okay. So, and it is more efficient than Salimans evolution. It is still highly parallelizable, but it can converge much faster with less efforts and less processing time. And It is very robust to parameters perturbation because we use divergence, and when this divergence is calculated, it will somehow nivell this parameter perturbation, and the cons of this is it depends on domain, because in their paper they prove that in some domains like general mover in Mojoko environment, they can evaluate it, and the simple random search works better than their policy. And also they say that in some tasks, gradient information is not useful for this. And so here we go to my part of the work, and the race from pixels is actually resembling a Darwinian evolution process or a conventional genetic algorithm with modified operators. So we create a new population of policies. So this is our agents, neural networks, and something. And then we evaluate them in environment, then select best individuals, then mix them with a special crossover operator, and change them with mutation, rinse and repeat, and you're done. The first thing to think is a selection operator, and this idea was taken from Uber Neuroevolution, and we use the deterministic tournament selection. So it resembles like gladiator ring in Rome, when you have some tournament and only the fittest survives and is taken to the next round. And also we have elitism like Caesar's loved ones, and they go to the next round without changes and without selections. They're the fittest. Mutation operator, we use safe mutation through rescaling approach from Uber Neuroevolution, but it was modified with binary search instead of linear search for the speed. So we make a binary search for divergence. And also here comes a very simple but still effective idea with crossover operator. Each neural network is a big nonlinear function and be considered as a big nonlinear functions with each layer that can be considered as a building block of a neural network. And here we present the layer blend crossover that is not that disruptive in case of divergence as conventional crossover approach like a multi-point or just blending crossover or something. So here we have truncated normal distribution from 0 to 1 with parameters mu and sigma squared. And we calculate mu as a fraction of fitness values for each individual. And then we sample a new parameter from this normal distribution for each layer of target child neural network. And somehow this got more good than conventional approaches. And here I can show it by testing. We tested this in some conventional environments from OpenAI, like Swing Robot, Acrobot, Mountain Car, and so on. I will not show this, it works pretty well. And these are simple tasks with simple neural networks. And for this, for good test, I use TORCS Environment, which is a racing environment. And you here have a racing car and racing track, and it is quite visual environment. So here we define the momental reward for every step, and as you remember, it is summed up after the agent crashes into the wall or his opponent or something. And as you can see, it can encourage the high longitudinal velocity. So it is the angle between track and the car heading. It discourages lateral acceleration, and it discourages excessive steering. This is a steering angle. And here in our experiments, we use these parameters. And the agent is defined like it takes as input the 64 by 64 color image. It is 3 RGB channels, and the agent structure is in here, but except of this one, here's 3 outputs for gas pedal, brake pedal, and steering, yeah, thank you. Here are track outlines on which we have tested it. So as you can see, they're different. Here's also just an OLAP, more and more complicated tracks. video. And here's the second video. On it, you can see how the same policy trained on this track acts in different tracks. And as you can see, it has very different visual appearance, and it still can work in every of these environments. In a moment, we will see how it works. Okay. Yeah, it is 64 by 64, so pixelated. And we will wait for... Actually, this one is the longest track, and it takes 11 minutes to complete. It is real time, and the speed is near 100 kilometers per hour. So it was the shortest, it finished. Okay, let's finish. Let's wait until one more lap finishes, and then next slide. Okay. Yeah, thank you. And so, okay. So it is a comparison with naive-endpoint crossover when the endpoints were taken for each point where the layers are stacked. And here you can see the child A, child B, and the parent A, parent B, and their child, and the fitness. And the closer to 0 is better. And so you can see for naive endpoint crossover, the most of the children have lower fitness than their parents. And that is bad because we generate like a degenerate offsprings that will not make a good sense to our task. And for layer blend crossover, for almost all of them, the child agent gets more fitness in between of these parents, or more than top fittest parent, which is really great. And I was surprised that such simple approach did such great result. Also, here's a comparison with conventional DDPG algorithm. It is an actor-critic synchronous, which I found in some implementation in Keras RL. And here you can see the same policy with the same neural network working on these tracks that I've shown, and it outperforms in several tracks. And on the longest track, it outperforms significantly in the number of episodes it takes to train. So it is rounded to 50 because in each generation it was a 50 agents. So also here's a comparison on the first track, how to evolve. And here's a comparison of endpoint crossover and the fitness, normalize it from 0 to 1. And as you can see, my algorithm converges much faster, in like 5 times more fast convergence achieved. Also, here's the cross-testing of policies. Like you have seen the same policy operating in different tracks. And here's each policy was trained on this track and evaluated on this track. And as you can see, it works quite good. And for some reason, it does not work that good on several tracks in combination. But I guess because it's lack of sharp turns in training data, and it just eventually crashes in a sharp turn. And that's why it does not work in these cases. Also, I performed an ablation study because my algorithm is consisting of different parts. It is mutation, crossover, and I checked it against a baseline of just random search of policy. Here you can see it's just a safe mutation from Uber, just my layer blend crossover, it is here. And here is a combination of random search and microsolver, and combination of safe mutations of random search and microsolver, which converges even more faster. And so it is made in the part of a joint project between my university and University of Berlin. And the final topic of it is to bring these agents to reality. We have a small-sized car in scale 1 to 10, and we need to bring these agents to reality, like it will run on the floor with some lane markings and so on. And also, the interesting topic is the applicability of crossover to recurrent neural networks, because Uber in their paper claims that it is applicable to any LSTM model and so on. So I'm interested in changing how will it work with microsolver, because with recursive neural networks, everything gets complicated. And with deeper networks, I hope it will also work well. In my neural network, it is almost 1 million parameters, and it works. And I also want to test it with more complex tasks, right, like Walker, Spider, and so on in Mojoko, because it is where the state of art is trained and tested. And now I will thank you for your attention and give you some useful links. And now the questions, please. I can share.
I can talk. Probably you can hear what I'm talking. Thank you for your talk. And who has the questions? Yeah, but I don't have a power to give microphone, so I will just mention who will talk and you can talk. Yeah.
Great. Thank you. Could you please summarize when it is better to use evolutionary methods in reinforcement learning, when robotics now from the current performance and limitations?
Okay. Thank you for your question. Okay. So the question is when it is better to use reinforcement learning and when is it better to use evolution strategies? Actually, there's no clear answer to this question because every time it appears in new state of the art with either evolution strategies or reinforcement learning, and it is quite a new field. But I can say that you definitely need to use evolution strategies if you have a lot of computers and you can highly parallelize it. So, for example, Salimans' evolution strategy, training time scales linearly with number of processors. So if you have a cluster with 1,000 processors, it will train 1,000 times faster. And for reinforcement learning, there are a lot of tweaks like asynchronous, actor-critic, and so on. And it is really good when you have your hardware. So you have a robot in hardware, and you need, for example, to teach it how to grasp things. And you want to deal with physics and don't want to bother yourself with bringing agent from simulator to reality, and then it's better to use conventional reinforcement learning. Thank you.
Thank you. More questions? Yeah. Hello, thank you very much for your talk. It was very good. I have a question about fitness. It was a bit unclear to me. Well, two questions actually. The fitness, is it the same as just sum of overall of the rewards?
Yes.
All right, cool. That's clear. And then the rewards, what was the motivation for selecting these specific rewards? It seems like a bit of reward shaping for the specific environment. Or is it?
Yes, actually. This reward was taken from a paper about DDPG algorithm applied to TORCS,
Right.
just to match their competition. And they proved that it is good for racing task requirements, and I just used it.
Oh, so it was fair comparison then.
Yes.
Yeah, thank you. More questions? Okay.
Thank you for the talk. It was quite good. I have a question about training with Neuroevolution. The question is, with conventional gradient descent, we actually split the data in training and evaluation, and we actually clearly see when the data is the network is overfitting. How do you prevent overfitting during the neuroevolution?
Okay, it cannot overfit in decent environments that are pretty big, because every step you introduce a random, and it acts like a really hard regularization for neural networks. But if you want to apply this technique to conventional imitation learning techniques or something, you definitely need training and testing like in conventional algorithms. But the power of regularization in this technique is really good. So it is robust to initial parameters, and it is robust to disturbs to parameters. So you can just apply a big mutation to an already trained agent, and it will still perform quite good. And as you have seen in video, it works in almost every environment, but trained only in one of them.
Thank you. More questions? Okay. Borys, thank you very much.
Thank you.
Thank you for your talk. Just 1 second.